Hello everyone. In this lecture, we are going to study the part number 2 of the chapter Electric Charges and Field. In fact, every neutral object consists of positive and negative charges. These charges are normally equal and opposite in an object, so the net charge on the object is zero. Net static charge can exist on the object by different methods. The first method is conductional electrification, which means charging by physical contact. For example, we take the case if the disc of an uncharged electroscope is touched by a negatively charged rod, then what kind of the charge get transferred to the electroscope? So that answer can be get from the method conductional electrification. So as if an uncharged conductor is touched with a charged conductor, the uncharged conductor may acquire charge similar to the charged conductor, which means that the disc and the leaf of electroscope will also acquire negative charge. It happens because some of the electrons are shared at a point of contact of the conductors. Second method is a frictional electrification, which means charging by friction, or in this case electricity produced due to rubbing of two suitable materials under suitable conditions. One of the rubbed material loses electrons and the other gain electron. So in this case, both the objects get charged. So in the case of the frictional electrification, transfer of electron causes charging of the material. The material which loses electrons on rubbing is said to be positively charged. The material which gains these electrons is known as negatively charged. Third method is charging by induction, the process by which a charged body make body charge without physical contact. So this is a method in which there is no physical contact between the charged body and the uncharged body. So in this case, there are the two types of the charges. The first one is the induced charges. The charges appearing on the bodies by the process of induction is known as induced charges. Second one are the inducing charges. The charges on the body which give rise to induced charge on another body without physical contact is known as inducing charges. So now we are going to learn about the basic properties of electric charges. The first property is the additivity of electric charges. We know that there are the two types of the electric charges, positive and the negative. Like charges repel each other and unlike charges attract each other. To calculate the total charge on an extended body, this is equal to the algebraic sum of charges in different regions of the body. Total charge on a body is a sum of all individual charges. Positive and negative charges are added like real numbers. Second property is the conservation of electric charges. According to the law of conservation of electric charges, the net charge, that is the algebraic sum of positive and negative charge in an isolator system, remains constant. Law of conservation of electric charges is treated as universal law because it has no exceptions. In other words, we can say that net charge can neither be greater nor be destroyed in an isolator system. It suggests that there can be transfer of electric charge from one body to another body, but there is no creation of charge in an isolated system. Next property is the quantization of electric charges. Existence of charges in discrete packets rather than in continuous amount. Quantization is a property of an electric charge which tells that any charge body can have a charge which is an integral multiple of the basic or elementary charge. So the formula for the charge Q is equal to plus minus of any, plus minus that it can be any type of the charge. So here n represent the integer can be positive, negative. E represent the elementary charge and its value is equal to 1.6 into 10 raised to power minus 19 coulomb. So this is the total charge and this is equal to Ne. So here the most important concept of this chapter, Coulomb's law of electric charges. This law states that the electrostatic force of attraction or repulsion between any 2-point charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the charges. To explain this statement, let us take an example. Here Q1, Q2 are the 2-point charges and small r is the distance between these charges. Then the electrostatic force of attraction or repulsion between two charges can be represented as, so the Coulomb's law can be represented as per its definition from the two rules that the force is directly proportional to the product of the magnitude of the charges. So we can take this as equation number 1. Force is inversely proportional to the square of the distance between them, that is the equation number 2. Combine both these equations, we get F directly proportional to Q1 Q2 divided by R square. Remove the sign of the proportionality, we get the answer F is equal to K Q1 Q2 divided by R square. Here K is the constant of proportionality, also known as the Coulomb's constant or electrostatic force constant. This Coulomb force is measured in Newton. Here are some important points regarding the Coulomb's law. That Coulomb's law hold good for the point charges relatively at rest. Coulomb's law is basically experimental law. Coulomb's law is applicable for macroscopic distances as well as very small distances. Coulomb's force is a two-body interaction, like it have interact between the two charges. Coulomb force decreases when the charges are placed in medium other than air or vacuum. So Coulomb's law gives the electric force between the 2-point charges, and this law follows the inverse square rule. Here small ka, that is the Coulomb constant, and its value is 9 into 10 raised to power 9 Newton meter square per Coulomb square. Q1 is the first point charge, Q2 is the point charge taken as number 2, and R is the distance between the two charges. Unit of charges. We are aware SI unit is coulomb, and we can also define the 1 coulomb. It can be defined as the charge which repel equal and similar charges placed at a distance of 1 meter from it in vacuum or air with a force of 9 into 10 raised to power 9 Newton meter square per coulomb square. There are some another smaller units of charges. First one is the microcoulomb, nanocoulomb, microcoulomb. And here is the scale to represent 1 microcoulomb into the coulomb, 1 nanocoulomb into the coulomb, and 1 microcoulomb can also represent in the units of coulomb. Comparative study of electrostatic and the gravitational forces shown in this slide. Electrostatic force can be attractive or repulsive in nature. Gravitational force is always an attractive force. Electrostatic force is a two-charge interaction force, whereas gravitational force is a two bodies of point masses interaction force. Electrostatic force is very large as compared to the gravitational forces, and gravitational forces is the weakest fundamental force in the nature. Electrostatic force is applicable in vacuum, yet it depends upon the medium in which the charges are kept, whereas gravitational force is applicable in vacuum, but it does not depend upon the medium in which the masses are kept. Both these forces obey the Newton's third law. So here are some questions regarding to the concept that we have discussed in this video. The first question, name an exact law of nature in respect of electric charges. The answer is law of conservation of electric charges, that electric charges are conserved. In Coulomb's law, on what factors the value of electrostatic force constant, that is capital K, depends? It depends upon system of unit used and also on the medium existing between the charges. Next question, two charges Q1 and Q2 are separated by a small distance. Satisfy the equation Q1 plus Q2 is equal to 0. What does it tell us about the charges? As they satisfy the equation Q1 plus Q2 is equal to 0, it means that both charges are of equal magnitude, but they are of opposite sign. So when they are add up, so their sum or equation is equal to Q1 plus Q2 is equal to 0. Next question, what is the change in the Coulomb's force between two charges when third charge is brought near them? As the Coulomb force is a two-body interaction force, so there is no change occur when the third charge is brought near them. Next is a numerical. Calculate the Coulomb's force between a proton and an electron separated by a distance of 0.8 into 10 raised to power minus 15 meter. So we have to calculate the attractive forces between the proton and the electron. We can apply the formula of the Coulomb's law. F is equal to K Q1 Q2 divided by R square. Here Q1 represent proton, Q2 represent electron. Both have the same amount of the charge in a same magnitude, but their nature is opposite. Electron is denoted by the negative sign and they are divided by the distance, that is 0.8 into 10 raised to power minus 15 whole square. After doing the calculation, we get the answer for the force 3.6 into 10 raised to power 2 Newton. Hope you understand this lecture very well. Thank you for watching. Take care.